Okay, today we're going to cover chapters 9, sections 1 through 2, and work on concept questions 1 through 6 and exercises 1 and 10. So I encourage you, go look at those problems, see how many you can do applying the concepts that you've read. I'm going to start with number 1 from the concept questions. Go ahead and take a look at that one, get a feel for it. Okay, so this is basically a definition of kinetic energy. So what is the definition of kinetic energy? All right, so K is defined as 1/2 mass times the velocity squared. All right, now if we triple the velocity, okay, the particle's speed increases by a factor of 3, then how does the kinetic energy change? So we see how it's squared. That means as v goes to 3v, the 3 gets squared, so we get a factor of 9. So that means we're going to get 9 times the original kinetic energy. So increased by a factor of 9. Just recognize that kinetic energy is linear in the mass, but quadratic in the velocity. Okay, number 2. Well, look at that one. Okay, this one is similar to this first one. It's also applying the proportionality of kinetic energy. So in one case, we have Ka, particle A, is 8 times the kinetic energy of particle B. And we have the mass of A is half the mass of B. So what is the velocity of A relative to the velocity of B? So let's expand this out. 1/2 MAVA squared equals 8 times 1/2 MBVB squared. Okay, the halves cancel. I don't care about those. Let's insert this mass. 1/2 MBVA squared equals 8 times MBVB squared. Okay, the masses now cancel, so I don't care about their exact value. And I see that VA squared is equal, if I multiply 2 across, then is 16 VB, or VA is equal to 4 VB. VA squared would be 16 VB squared, squaring everything. And so we see that the ratio of VA to VB is 4. So again, both these problems are applying the proportionality of kinetic energy. Okay, let's move on to discussions of work. So that's an exercise or concept question 3. So let's look at concept question 3. Go ahead and take a look at that. Okay, here we have an elevator that's being pulled up by a single cable. And the elevator, so the tension's up, tension's pulling up. The elevator is moving up, though it is slowing down. So its acceleration is opposite its velocity, in this case down. But when we're asked what is the work done, is the work done positive, negative, or 0, it doesn't matter what your velocity is. It doesn't matter what your acceleration is. It just matters what your displacement is. And so our displacement, our delta S, is up. The elevator is moving up, though it's slowing. And work, in its most basic, for a constant force, is just the force times the displacement. Okay, and these are in the same direction, so I could put Fs there to emphasize it's in the same direction, and they're like, well, along the same coordinate, but they're in the same direction, so they're positive because they both are pointing up. So it's going to be positive that, which means this is greater than 0, or it's positive. Okay, apply the same idea to problem 4. Okay, here we have a box being pulled across the floor by tension. Is that tension doing positive work or negative work or no work on the box? Okay. Again, it doesn't matter the velocity of the box. It doesn't matter the acceleration of the box. It just matters the displacement of the box. And the box does have a displacement in the direction of the tension, so the work by the tension in this case is also greater than 0 because they point in the same direction. All right. Let's go ahead and take a look at number 5. This one's an intriguing question. Number 5. So what's the main idea on this question? We're trying to find, we're told the equal forces are pushing these objects equal distances, and you're trying to compare the kinetic energy of this really heavy lead cart versus this really light plastic cart. Well, what is the main idea? Okay, I hope you saw that the main idea is that force times distance is work. Force times distance, or displacement. Okay, and in both cases, they're the same. Equal forces push the objects equal distances, and that, by the work kinetic energy theorem, is equal to the change in kinetic energy of the particle, which means our particle, the plastic cart, has the same increase in kinetic energy as the lead cart, and they both started from rest, which means they both have the same kinetic energy at the end, because it's equal forces and equal distances. So what appeared to be a pretty complicated problem, that if we actually tried to apply kinematics to, using force to find acceleration and then using our kinematic equations to find a final velocity, we could have done it, but it would have been a pain in the rear. But we see with this very powerful definition, this very powerful fundamental concept, I should say, that we were able to solve that fairly quickly. Okay, number 6 now. Take a look at number 6. All right, so here we have a particle is moving to the left. So our particle is moving this way. Here's delta S. And a force is pushing it to the right. Okay, but it still continues to move to the left. All right, so here's our force. Is the work on that positive, negative, or 0? Okay. It's going to be negative because the force is slowing this box down, but more so it's pushing this way, pushing to the right, the displacement to the left, so those are opposite each other, which gives us a minus sign, so the work is less than 0. Okay, very good. So now let's go ahead and move on to the exercise 1. Okay, so this is a definition, again, of kinetic energy, but this kind of gives you a feel of real life experiences. So the kinetic energy of a bullet relative to the kinetic energy of a running student. Okay, so kinetic energy of the bullet is equal to what? You get 1/2 mass of the bullet times the velocity of the bullet squared. You plug that all in, 1/2 times the 0.01 kilograms times the 500 meters per second squared. Okay, the very small mass is compensated by a very large velocity, which is squared, and you end up with 1,250 joules of energy, kinetic energy. What about the student? What is the kinetic energy of the student? Well, if you plug in the numbers, same thing here, but a 75 kilogram mass and a 5.5 meter per second speed, you end up with 1134 joules. So similar. So a bullet going 500 meters per second and a person, student running 5.5 meters per second have about the same kinetic energy. All right. Now let's look at exercise 10. Okay, so the first part of this question, how much work is done by gravity, is very similar to what we've already done. It's a definition of work. And so this the crane via tension is pulling up on this beam, okay, pulling up on this girder. It's a big beam, and gravity is pulling down on it. Okay. It does move upward, so its delta S is upward. That's 3.5 meters. With just that information alone, can we find the work done by gravity? There we can, because we know the force of gravity. The work done by gravity would be the force of gravity, mg, times the displacement, and that delta S. But they're opposite each other, so I'm going to get a negative sign. So it's going to be a negative number. And I can calculate that, and it ends up being a negative 2,500 or 25,725 joules. A fairly large number, okay, because the mass of that girder is pretty large. All right. So that's the work done by gravity. Now, how do we find the work done by the tension? We're not given the tension. What we are given is an initial speed and a final speed as it moves upward. What does that give us? What does that tell us? That gives us a kinetic energy, a difference in kinetic energy, which is related to the total work done on the beam. Okay, so we can say that the work done by tension, which would be positive because it's in the same direction as the displacement, subtract the work done by gravity, which is negative. That's the total work done. That's going to be equal to the change in kinetic energy of this beam, which would be K1 minus K0. Now we can calculate that. I know how fast it's going to start. I know how fast it's going to end. So I do 1/2 mv1 squared minus 1/2 mv0 squared. I can find that. If I do, that's going to be equal to 187.5 joules. Okay, and then we can just subtract off what we found, or add the gravity to the other side, giving us the work done by tension, which will be positive because the kinetic energy change here was positive, it's sped up, and the work done by gravity was negative, but we subtracted the other side. We chose to indicate that negative sign by putting it here. So we have that, and if you add those together, we get 25,900 rounding up. So that's the work done by tension. And it is greater, and the more important thing is greater than the work done by gravity, because it did go upward. Okay, so that's the main idea. Some things we see here from this reading. The definition of kinetic energy, a basic definition of work. We'll go into this in more detail in the next class. But also some qualitative features. When is work positive? When is it negative? And then how can you relate the work and the kinetic energy together?